Okay, in this video, we're going to start our unit on gas interactions, and in particular, these different gas laws that dictate how gases move and how they respond to different stimuli in our environment. To do that, we need to first talk about the kinetic molecular theory, okay? And what this is going to do is try to explain how and kind of why gases move the way they do, all right? So parts of this theory, first of all, molecules of gas move rapidly in constant linear motion, okay? We're basically just identifying that when gases are moving, they're not curving, they're not stopping, they're not standing still. It's a very fast movement and it's constantly linear, okay? That then correlates back to the next one where they can change direction, but it has to happen through a collision. So either they need to strike the walls of their container, they need to strike another molecule to cause some sort of collision that will change their direction, okay? This also kind of leads into the idea that gases are going to expand to fill their containers completely, okay? Because they can move constantly and linearly. Now, looking at this idea, we have little arrows kind of pointing direction, but this little clip here kind of shows what we mean about that. This constant chaotic motion inside these gases. And we've actually have some simulations we've seen before on this too. The third part of this is kind of the biggest one, is we're going to assume that gases act ideally, okay? We'll talk in this unit about real gases and about ideal gases. And we often are going to say that real gases that we work with in a laboratory setting or our day-to-day lives act ideally. And when we say that, we're not just saying that they're very nice people and they're taking care of their business. We're saying that they actually have certain parameters to them that match up with what we call an ideal gas, okay? So to talk about that, we should really identify what are these things that make a gas ideal, all right? So ideal gases are ones where there are certain aspects of our physical universe that we kind of ignore to make them mathematically ideal, all right? The first one is that the collisions between the molecules are completely elastic. Now, you guys most likely haven't had physics yet. The term completely elastic has meaning in the world of physics, and what it means is that there's no kinetic energy lost as you collide, okay? In the macroscopic world of big objects, when things collide, there's always a loss of kinetic energy to heat, build up, deformation, that kind of stuff, elastic kind of things. But because these particles are so tiny and they're moving so fast, when they collide, essentially they don't lose any kinetic energy or it doesn't go anywhere else. So because of this, we don't need to track changes in kinetic energy over time for our gases. Second one, we're going to say there's no attractive forces between molecules of a gas. Okay, and you might be thinking IMF, and you'd be right here. So because gases have broken free of IMF, and they're moving so fast, and they're so far apart from each other, we essentially say that IMF doesn't exist. So again, this is another thing that we can mathematically exclude as we look at how gases behave, is that the IMF isn't playing a role here. It's not attracting them, it's not holding on to them, that kind of stuff, okay? Now the last one is a tougher one, because it says that the particle itself has no volume. Okay? But there's still a large amount of space between particles. Essentially what we're saying here is that the actual diameter of the atom is so small in comparison to the space between one atom to the next atom that the diameter of the atom doesn't add to the math, or it's negligible. Okay? To give you an example in the macroscopic world, if I said I want you to calculate the distance it is from Egan High School to Walt Disney World down in Florida, okay, nobody is going to go out and measure the distance it takes you to walk from the front door of Egan High School to your car. Okay, sure, that's distance you travel, right? It's, you know, it might be 50 meters, it might be 100 meters if you park in the back of the parking lot, but that extra 50 meters or 100 meters isn't factored in when you're going to factor in this gigantic trip down to Florida, right? You just will never do that. Same thing here. The actual size of the atom doesn't really play a role. So when we talk about the math behind it, we can just look at the space between one atom to the next atom, not having to factor in their actual size. Okay? So those are the three big ones. And again, let's talk about that far apart kind of idea. Now, one thing that's really nice about our physical world is that real gases that we actually measure and work with and deal with in our everyday lives, they act ideally under normal temps and pressures. So what is normal temps and pressures? Basically, normal temps and pressures are our environment, okay? So we're lucky that in our environment, it is cold enough by temperature and the pressure is low enough that these real gases that we interact with act ideally also, okay? So there's no mathematical difference between how a real gas acts and how an ideal gas acts under these normal conditions, okay? However, we can get real gases to act differently if we put them under extreme conditions, like extreme cold or extreme pressure. And we'll talk about that at the end of our unit, okay? So for now, we're just going to say gases act ideally. Now, gases themselves, let's give a quick reminder. This is not the first time we've seen this slide, so I'm just going to kind of go fast through it. How they work in terms of filling their space, being compressible. All these properties are based off this kinetic molecular theory, okay? We have the 4 variables that dictate gases: pressure, temperature, amount, and volume, and we're going to talk about each one in this little video lesson. And then remember, this is a big one down the bottom, the type of gas or formula does not matter, okay? So if we're talking about carbon dioxide gas or oxygen gas or a mix of the two, they're all going to act the same, all right? And that's kind of a big concept that we don't need to say what type of gas it is to know what it's going to do, all right? So first of all, volume and amount. These are 2 things we already know. Just some quick reminders. Volume is a space occupied by a substance, okay? For us, that means the space between 2 gas particles now, okay? And then reminders that gases are going to expand to fill their containers. So when we talk about the volume of a gas, what we're really looking at is what is the volume of the container they are in, all right? So if you have a balloon that can hold 2.5 liters of gas, that's the volume of the gas because that's the size of the balloon, okay? Now, amount, that's our moles, okay? We can't count individual atoms of a gas, so we're going to group them back into moles, talking about them as a mole at a time, as we did before, okay? Now, in this unit, it's a little bit weird. I know we've been using MOL as our kind of abbreviation for moles, but when it comes to gases, we give them a new designation. We call that N, okay? So as you start looking through this unit and we see N, that your brain should start going towards moles. That's the amount in moles, okay? Pressure is not brand new to us, but we haven't talked about it in a lot of detail, so we should probably hit it and kind of explain what is pressure, okay? Now, gases can create pressure, and that pressure comes from the strikes to the surface of our container. So inside of here, as these gas molecules are bouncing around and hitting the container, they're creating pressure because every collision with the walls of the container has a force acting on it, which creates pressure, okay? So if you get more particles, so if we have more things inside of here, or we get them moving faster, we can create more pressure. We'll spend a lot of time talking about collisions in this unit and how if we can just get more collisions or faster collisions, that we can increase our pressures, okay? Now keep in mind that pressure does have a unit to it or a label to it. And unfortunately, we actually use 3 different ones in the scientific world. Atmospheres is the SI unit, or the one that is the standard one. However, millimeters of mercury is very common, especially in the earth sciences, because this is probably the first one that we worked with. And finally, pascals, or often known as kilopascals, is also very common, especially in the meteorology world, where we're talking about pressures that way. So for us, knowing all 3 of these is going to be kind of part of our need here. Now, converting between them is pretty simple. We're going to base off of 1 atmosphere pressure. So for every 1 atmosphere pressure, we have that 760 millimeters of mercury. And then 1 atmosphere pressure is 101.325 kilopascals. Okay? This one's easy to remember because we have a radio station that's very similar to that in the Twin Cities, 101.3 KDWB. So it's a good one to work with because you hopefully can remember that number based off that radio station already. Okay? So it's kind of on your own to be able to convert between these. We're not going to practice that because that's actually just simple dimensional analysis that you already know, okay? We also need to talk about atmospheric pressure, or what is going on around us, because when we have a container, let's say we have a container like this, if there's pressure on the inside, what's going on the outside of that container, okay? And it's worth our time to acknowledge the fact that anything that we work with has atmospheric pressure around it, okay? So we're talking about this pressure that's exerted by the force of gases on the atmosphere around us. The air around us has weight, and that weight actually pulls on us and actually pushes on us because there's pressure there, okay? So for example, if I have a gas inside a cylinder and it has a piston head which is movable left to right, the atmospheric pressure is going to be pushing on it inwards. The pressure from the gas particles on the outside pushes outwards, and they're going to find some sort of balance or equilibrium between the two where these 2 pressures equalize each other. When we talk about millimeters of mercury, that's just kind of the same idea. The atmospheric pressure pushes down on mercury, which then fills a column under vacuum conditions. And because of a certain amount of gravity, the height at which this pressure can push down, forcing it to go up this narrow column, that pressure or that height can be measured which then creates the unit of millimeters of mercury, or in this case, it talks about centimeters of mercury, okay? So we still have this pressure we're always dealing with. We're going to talk about that a lot in this unit because there's going to be a balancing act between the pressure inside of some things and the atmospheric pressure pushing back, okay, as we go through this unit. But just keep in mind that at all times we do have to work, the atmospheric pressure is present on all of our objects. Now, temperature, again, this is not new to us. We're going to go kind of fast through it. Remember, temperature is measuring the average. You might want to underline that, average kinetic energy of a system, okay? And remember, kinetic energy is moving energy. So we can start to relate that back to the faster a particle moves, the more kinetic energy it has. The more kinetic energy it has, the higher its temperature. So things that are warm and are moving fast have high kinetic energy. Things that are cold and are moving slow have low kinetic energy, okay? Usually, we can just talk about temperature. Like, okay, this is high temperature. So in our brain, we should go to, oh, it's high temperature. That means the particles are moving faster, okay? Or, oh, this is low temperature. That means the particles are moving slower. What that's going to let us do is say, oh, if they're moving slower, that means there'll be less collisions, which means that it's going to generate less pressure. So there's going to be a kind of like a coordination of thought there, all right? All right, so that is temperature. Now, we're going to dive into what's going to happen to a gas if we change one of these four variables, okay? And that's going to be the next segment in our unit. Thank you.